Okay, so this next video is on nuclear stability. So we're talking about why the nucleus is stable. So we have to start thinking about what is inside of it. So we start thinking about the nucleus, we have neutrons and protons. Now neutrons have no charge and protons have a positive charge. So then we can think, well, why doesn't the nucleus rip apart? I mean, we have positive protons, which are trying to repel each other because positive charges and positive charges have the electrostatic force of repulsion. So there should be this force trying to kind of pull the nucleus pull the nucleus apart. So scientists then were like, well, therefore there must be another force acting in that nucleus. And that force must be an attractive force trying to pull this in together to counteract that repulsive force. Okay, and scientists then discovered this force and called it the strong force. Now the strong force is actually the strongest force, but it has a very small range, okay? Its range is actually only around about 10 to the minus 15 meters, so around about the size of a nucleus, okay? And the strong force acts between nucleons. Okay, so it acts between protons and neutrons. Okay, and that attractive force between the protons and the neutrons is what holds this together to counteract, okay, and balance the electrostatic force that's trying to pull them apart. So then we start looking at, in terms of our elements, if I go to the periodic table and I plotted all of my stable isotopes for my number of neutrons versus my number of protons, I would get this little blue curve like this. Now what you'll notice here is that at the early elements, okay, so these light elements, so small numbers of protons, okay, the number of neutrons is almost equal to the number of protons. But as we start to get to higher elements, okay, so larger elements, heavier elements, ones with a greater Z number, so a greater number of protons, we actually start to need more neutrons. Okay, so with this we start thinking, well, why is that? And we're going back to those forces. Okay, the more protons we get, the more electrostatic force there is. Okay, so we're going to need so much more strong force. And so to add more strong force in, okay, without increasing the electrostatic force, we need more neutrons. Now these are stable isotopes. We're going to start discussing unstable isotopes. Again, there are unstable isotopes go through a radioactive decay to become more stable. So these are ones here in the red and the orange. So just to recap, heavier elements, okay, the N number is greater than the Z number. Okay, the number of neutrons is greater than the number of protons, so they have more strong force. So for example, if we look at polonium, we have the proton number is 84, the neutron number is 209, take away 84, so we have 125, and we can see that 125 is much bigger than 84. We can also look at uranium. We're going to look at uranium when we do nuclear fission, and we can see that proton number is 92, the neutron number is 238, take away 92 to leave me with 146. Okay, so that's our heavier elements. The N number is greater than the Z number. For those lighter elements where I don't have so many protons, okay, there pretty much only needs to be an equal number or almost equal number of neutrons in there for them to be stable. All right, in this case, we have helium, so 4, 2, so we can see protons and 2, neutrons is 4, take away 2, so also 2, so we can see here that N is equal to Z. Whereas if we look at sodium, sodium is 1123, so protons are 11, and neutrons are 23 minus 11, giving us 12. So again, the N number is almost equal to the Z number there. So when we deal with our unstable isotopes, okay, we usually have either too many protons or too many neutrons going on, and we want them to decay to form onto this stable line down here. So that's what we're going to deal with when we look at nuclear decay.